So Chris Chickadel, also from APL at UW. Please go ahead.
All right, thanks, Henrik. Yeah, I sit just down the hall from Morteza when I am actually in the lab. All right, so I'm gonna give a overview of some recent work actually done by a postdoc that Andy Jessup and I advised. It's on the thermal signature of residual foam and breaking waves. So a lot of the themes that have been spoken about today, especially Morteza's actually introduction or work, serves as a nice introduction for why you might care about whitecaps. And we're going to look at it in a little different way. So this is kind of a departure in that we're going to use thermal imaging. In this image on the top left, this is a thermal image of actually the field in which waves have been breaking. In the image, dark is cool, relatively cool, light is relatively warm. And you see this highly complex modeled surface with respect to temperature. The temperature range between the sort of light and dark is about 1 degree C or so. The imaging mechanism of thermal imaging is actually looking at the cool skin. So the long wave IR optical depth of the camera that was used to take this image is about 20 microns. It's seeing the very, very thinnest skin at the surface. The reason we see such apparent temperature variation is because of a phenomenon called the cool skin. So in the upper right, this cool skin is denoted by this dashed line below the free water surface. And there's a breaking wave that's represented in the middle here. This thin skin, which is sort of the viscous layers, about 1 millimeter thick, and it supports a temperature gradient that cools towards the air-sea interface because of the outward heat flux from the ocean to the atmosphere. The temperature difference between the interface and the bulk water below this cool skin is of order tenths of a degree, and that's pretty typical. Because of the thinness of this layer, it's easily disturbed by turbulent straining bubbles rising to the surface. So in the case of a breaking wave, as demonstrated in this image, at the wave crest and in the wake turbulence behind it, it would look relatively warm, whereas in the undisturbed water in front of the wave and some time and distance behind the wave, when this cool skin reforms, it would look cool. The recovery time is of order seconds to minutes, depending upon the heat flux. Our motivation for looking at whitecaps is somewhat interesting. That the image I showed you before was just disturbance without bubbles. However, in observations, a decade and a half ago or more, what was noted is that when thermal imaging was applied to the open ocean under whitecapping conditions, what was noticed is that the active wave breaking, so in this sequence of images showing the passage of an active wave on the upper left, and thermal imaging, upper left is before the wave arrives. This is the active wave. It looks warm, and that's because of the disturbance of the cool skin, showing the bulk water below. Of course, this is also aerated water. What is interesting is that, and what some had noted is that the plume or the foam that was left in the wake, this sort of passive foam, cooled sometime after the passage of the wave, whereas it would still be visible as a bright patch in normal imaging. There are some speculation about what's going on. We've done some investigation, and it looks like as some had expected, enhanced evaporative cooling in the foam layer that's exposed to the surface promotes a very rapid cooling relative to the cooling of the undisturbed water around it. What's interesting is trying to understand what this momentary delay is, whether it was just the cooling mechanism or something physical to do with the bubble plume generation. We see that here. Another example of this residual foam showing more detail in that the patchiness in the thermal imaging shows that some parts of the plume of the residual foam were actually cool, while others were not cooled yet. So it suggests there's some heterogeneity in the processes at work. Further, Andy and I had a recent graduate student, Roxanne Carini, who used this phenomenon to actually separate between active and passing foam, active and passive foam. So in this movie, in the upper panel is a time series, is a video of thermal imagery from the field research facility in Duck, North Carolina, taken at night. And you can see bright wave crests as waves are approaching the shore and breaking. In the box below, the two boxes below, it just shows a zoom in of the bright wave crest. She was able to use a thresholding technique to differentiate between this active foam. And if you look in behind a passing foam, she's highlighted the regions that have cooled below the sort of ambient water around it. And you can see this wave that's just passing, that there's actually quite a dramatic appearance of this foam that cools sometime after the passage of the wave. She used this in this right-hand panel. She used this to estimate the dissipation by isolating that active roller using the Duncan 1981 roller length estimate of energy dissipation in a wave. And this is just a time series. So from top to bottom, time increasing in cross-shore distance of the energy dissipation estimated just by measuring the cross-shore extent of the roller and applied to Duncan's model. So it's pretty clear, and everybody else has already shown this, and I think Luke and Morteza especially have shown some compelling evidence of why you really care about whitecaps, because they're indicative of the sort of bubble plume processes, which I haven't talked about, but they have, and energy dissipation, which they have. And of course, and Luke, I think, did a good job of presenting the factors of the importance of air-sea mass, momentum, and heat flux, and aerosol production in whitecaps. Work by Callahan to exploit the visible signature of whitecaps noted that the residual foam at the surface, the decay time for what it exists at the surface, is related to the plume time below, right? So it's related to the bubbles that are produced in a wave breaking. And that's shown in this plot to the right. What's interesting, however, is he noted that there is a significant dependence of this decay rate of the surface foam to the decay time of the bubble plume below. Whereas if you have basically surfactant-free conditions, you get this very nice approximately 1-to-1 correspondence of decay time in the foam to decay time in the plume. Whereas if you add surfactants, you exaggerate that, you increase the scatter, and by removing that easy or sort of direct relationship, you have weakened some way to exploit this to be able to say something about the bubble plumes that are produced. So our questions are, one, basically, how is this cooling foam related to the bubble plumes that are produced in breaking waves? Like visible foam, do surfactants affect this cooling foam signature? And what we really want to do is be able to utilize this fairly straightforward and convenient imaging mechanism to exploit and infer breaking wave properties. So to do this, we set up some experiments in the Washington Air-Sea Interaction Research Facility called WaveSurf. This actually is a repurposed NASA flume that was called NASURF and reinstalled in the hydraulics, in Harris Hydraulics Laboratory in the University of Washington. There's an image down below. We filled it with salt water, artificial salt water, to about 30 parts per thousand. We have a programmable wave maker, a piston type wave maker, and a series of cameras, including an IR camera looking down at the surface, a visible band foam camera, also bore-sighted with that IR camera, and a side viewing camera mounted to observe the plume. We used a focus wave packet technique, focus wave packet technique to generate repeatable wave breaking in the imaging region, the test region. We were able to vary the air-sea temperature difference by heating the water. So this has a water heating unit, which allowed us to simulate some modest variation in the air-sea heat flux. And we simulated, we varied the surfactant concentration between, in this case, I'm going to show just no surfactants and sort of like Adrian Callahan had used in his laboratory experiments, a roughly moderate productivity region in the ocean at 200 micrograms per liter of Triton X100. So first, we're going to look at the visible imagery. On the left is the side view image of the bubble plume as a wave is breaking. The top image is shown on the right. Breaking wave, you've all seen lots of breaking waves, so I'm really not going to talk about that much. We tested 4 different wave packets and many runs each, totaling over 450 breakers observed. We varied the breaking by varying the integrated slope of each wave packet. This is following Lowen. And that corresponded to a range of total energy dissipation of 74 to 105 joules per meter. And the actual wave breaking height in these cases were sort of 10 to 15 centimeters. Naeem proceeded through analysis to quantify the foam, the bubble plume, and the surface foam through a simple threshold analysis. And this was pretty straightforward. We were able to, of course, have full control over the lighting. So we just used a constant threshold, and it was fairly invariant. So you can see these upper panels and lower panels show the side view, the bubble plume as it's developing, and bubbles are rising, and that bubble plume is dissipating from top left to bottom right. This is the thresholded image, and likewise, the corresponding surface residual foam and active foam as it's evolving through time. I think what's interesting to point out, and has been shown in some simulations and data in this conference, is of course the initial wave breaking and secondary splash up, which creates, in this case, 2 distinct foam or bubble plumes, and that's corresponding to surface signature of foam that is banded in this case. This is going to come into play later. Following the work of Callahan, in an effort to reproduce it to make sure that we're getting consistent results for the visible portion, Naeem employed an exponential decay fit to this foam fractional area, which is in the top series of panels. There's foam fraction coverage. So this is the surface over time for, and this is the integrated, so the ensemble averaged with no surfactants in blue, that's this trace, and the with surfactants in red, and it's increasing in wave slope, so breaking strength, as you can think about from left to right. The vertical lines are e-folding timescales from those exponential fits, and you can see that there is a clear difference between the no surfactant case, which is shown in blue, and the with surfactants cases, so which is shown in red. It's most clear when you have stronger breaking, where more bubbles are generated. You can see the enhanced longevity of the surface foam. The plume area, right? So the submerged bubble plume area, time series is shown, or time series, ensemble time series is shown again with wave energy increasing from left to right. And you can see very little difference between with and without surfactants. The e-folding timescales estimated from each of these curves nearly lie one on top of the other. Plotted at each of the individual cases of the plume decay time, this tau plume decay, and the surface foam decay time. So again, these are the e-folding time scales. Really elucidates the difference between surfactant and surfactant-free cases. Again, no surfactants are shown in blue. The cases without surfactants are shown in blue, and the cases with surfactants are shown in red. Each of the larger symbols, small symbols are individual runs. Larger symbols are the ensemble average for each of the slope we tested, each of the wave slope packet slopes we tested. Effectively, the increase in slope and with dissipation is sort of increasing outward, indicated by that arrow. And you can see this large difference, right? You know, a 30% or 50% difference depending upon the strength of wave breaking, right? So it's a really clear implication of the addition of surfactants for the visible. Now, in these sets of images, there's, to reorient you a little bit, I'm going to show the time series of the side view, the top view of these are both visible, and the bottom right is going to be the infrared image. Like the example IR images I showed before, the cool is relatively dark, and warm pixels are relatively light. In this image, Naeem has overlaid the outline of and the corresponding outline of the visible foam identified from the top view, and it's remapped to the IR image. So I'll play this as it goes. In this case, as it goes pretty quickly, I'm gonna manually scroll by. So in the beginning, when the wave is just passing by and you have surface disruption, and you can see bubbles forming, there's a bubble plume initiated, bubbles already rising to the surface near the front, or formed at the surface near the front. You can see a strong disturbance of the cool skin, which shows warm relative to the undisturbed bubble or undisturbed surface in front of the breaking wave. Sometime later, not very long later in this case, the residual bubbles at the surface, which correspond to this rear plume, is indicated here in the IR image, is still relatively warm, though you can actually begin to see some spots where it's starting to cool, right? These are individual bubbles and small bubble patches. As you increase through time slowly, you can see that patch cool relatively rapidly, which roughly corresponds, though it's being deformed and stretched here, to the absence of large bubbles in this case. Large bubbles you can see in this forward plume are highly reflective in the light. These are mostly small bubbles. And it stays cool even as the rest of the residual foam. Clearly, when there's no more bubbles adding to the surface, and now it's stretched and disaggregated, many of the bubbles have already dissipated. You get basically just cool foam remaining at the surface. Play that again. You can just see that all. Doing the same analysis and using the visible image to identify the regions of the foam in the IR image at the surface, Naeem tracked the temperature variability of the foam over time. Again, these are ensemble averages. And again, the increasing sort of breaking strength, increasing wave slope packet is increasing from left to right. And the ensemble is shown, the mean of the ensemble is shown by the solid line, and the sort of shaded area is the variation. Again, with and without surfactants, blue no surfactants, and red with surfactants. And you can see Naeem has identified a time here past the peak. So this is when the wave had effectively past this peak temperature. So the temperature is increased. He's reset it so that the peak temperature, the disturbed temperature, is set to near zero, approximately zero. It gets rescaled. And as it's decreasing, which is the cooling of the foam through time, and dissipates, you can see that in general, there is not too much difference between surfactant and surfactant cases. As you increase the wave energy, you're also increasing the time that the surface foam is maintaining a higher temperature. All right. I'll next discuss what I think is what we think is going on. He's indicated a time at which the cooling drops below a certain threshold, and that threshold is actually the noise level of the camera. So that's when we can reliably say we see some cooling of this foam at the surface, right? So it's the initiation of cooling at the surface, though it continues cooling, right? And you can see as you increase the wave slope, the breaking strength, presumably the bubble production, that is also increasing over time, or with wave energy. Likewise, the plume area fraction is shown below, and it's the same plume decay time that shown, though Naeem has zoomed in just to emphasize this time scale of the plume. So our conceptual model is that the shown in blue would be the plume decay time, or the area of the foam under a surfactant-free case, such that if you examine a place on the ocean as a wave was passing by, a breaking wave was passing by, and breaking surface foam was generated, or a bubble plume was generated, it would reach some maximum and then decay over time. The corresponding temperature of that surface patch would increase as that water is disturbed. We theorize that as the bubble plume that's generated, that's initiated below, rises and continually mixes that surface in that warmer water and continually disrupts that surface, we would expect to see some period of warm temperature that was reflected in the bulk water below, at which point the bubble plume would cease, or the dynamically important parts that, or the relevant parts of the bubble plume that are generating surface straining and stressing and disturbing, so probably large bubbles that rise relatively quickly. Once those have ceased to rise, we theorize that that's where this cooling starts. And we can somewhat test that by plotting the total plume time, the total plume time. So that's this total plume time is the time from initiation to some e-folding time. We do that because that's a more consistent comparison with our cooling time, and the cooling time, to remind you, is from the initiation of wave breaking to sometime when the bubble plume stops influencing the resupply of bubbles to the surface foam. So if that was clear, the correspondence between this total plume time and the cooling time that we've identified in these cases has a very nice, apparently linear, though not one-to-one correspondence, as Adrian Callahan had noted with visible imagery. But we do see the same dependence on the increasing in the wave packet slope and thus the dissipation. So with increasing wave energy or breaking strength, we see an extended cooling time as we see an extended plume time scale. What's interesting is we didn't really see a strong dependence on the surfactants versus no surfactants. So this is good news for us if we want to use this to do some, if we want to infer some information about the bubble plume, like the bubble plume time scale, decay time scale. And I mentioned before that we did vary the air-water temperature difference, which is a modest way to influence the air-sea heat flux. And this is a scatter of all this data that's shown on the left plot. On the right, color-coded by the air-water temperature difference, such that we had 0 air-water temperature difference, the air and the water are the same temperature, up to the water being 2 degrees C warmer than the air temperature, which you have very strong outward heat flux. And we basically see no dependence. So that's also good news. Again, stress this is sort of a moderate case, but this is indicative of lots of the air-sea heat flux conditions we would see in the open ocean. And again, that was just to remind me to say those two things. So as has been shown in all those cool simulations and models, the wave breaking is not a uniform process spatially and temporally. And in this case, instead of an individual image, what I'm showing is the composite images, all of sort of 40 to 50 tests for this one wave packet slope, showing in this case, the sort of double plume that's generated as this small wave is breaking in our facility. And what you of course notice, it's highlighted much better in these now ensemble averaged images or movies, that the patchiness is very distinct and it's repeatable and corresponds to different patches of cooling. Again, this is relatively cool, where there is a strong patch of foam corresponding to this this rear patch of foam, and that evolves over time. It gets a little more noisy as the decay of foam is not a very clean process. What we are interested in knowing is, can we, because we have now a way to examine the time scale of a plume somewhat isolated from the breaking event, right? Much of the work has been looked for visible imaging and whitecap coverage, is you're looking at an integrated whitecap coverage, such as a single wave or multiple waves, right? There isn't a good mechanism to look at individual patches. But because we're using this IR imagery, we have some way to segregate those a little more distinctly. And can we use that to our advantage to actually look at the heterogeneity of wave breaking, of the wave breaking process? So Naeem did exactly that. So using those ensemble averaged data, he was able to automate a technique to follow a patch of foam that's outlined in this red box in this top view, and track the corresponding patch of the surface in the thermal view. And likewise, though this was a little more difficult because of the overlapping and convoluted nature of the straining of the bubble field as the wave packet is going by, also mapped the bubble plume that was corresponded roughly to, or exactly to, this foam patch. So the idea was, can we get some more finely separated information of bubble plumes within a breaking wave, and how does that correspond to the cooling signature we see? So these are just like the images I showed before of the surface foam temperature and the plume area fraction. And they show very similar sorts of patterns, but basically indicate that, yes, indeed, we can do this tracking. And what he's showing in this lower, so you see very similar plots where you have what looks like an increase of the time scale to cooling as you increase the energy in the breaking wave. Likewise, what he's showing here in the solid line is the original data of the examination of all of the foam, or all of the bubble plume area that's viewed by the camera versus the time scale of the single tracked foam. And it looks, well, we can't track it for quite as long as we can the total surface, because it starts to move out of the area and also starts to merge with the other bubble plumes, right? So it becomes indistinct. However, you can see that the area fraction is both increasing and its decay time looks like it's increasing. The plots are a little, I'm actually plotting Naeem didn't actually plot the cooling so this is now just looking at the foam patches, or a single foam patch, the aggregate data. He's plotting the maximum depth of the foam here. That was what we determined was a cleaner signal than looking at the decay time, which you can see it was a little tricky, would have been a little tricky to pull out from the data. But what we see is, we still see a strong relationship between the cooling of that patch that corresponds to the maximum depth, in this case, of the bubble plume. This is all the foam patches. That's just to show you. And then, sorry, yeah, I was mistaken when I was saying this is actually the patch, the tracked single patch. So actually, it becomes much tighter. So you can see that when you're examining the whole wave, there's lots of scatter because of you're tracking all these patches in part. You get a much tighter correspondence between the plume depth and the foam patch when you actually are segregating a single patch and examining that. So that gives us some hope that we could use that in the future to examine the heterogeneity of the plume structure underneath a breaking wave. This is just an example of Naeem then tracking multiple patches and showing the time of the time evolution of the temperature of the foam between those. So conclusions, we definitely see a cooling timescale as proportional to the bubble plume timescale decay in waves. And the cooling scale seems to also correspond and increases, the timescale increases with the breaking wave strength. It's not significantly affected by variations in heat flux or surfactants. And certainly we can see something about the variability in the plume structure. We have some measurements that are planned for about this time next year, where we're going to actually move up to a larger wave tank. This is the OMSET wave facility in New Jersey. It's a natural saltwater tank. We can generate field scale waves, right? So the wave that's breaking in this left image is sort of 75, 70 centimeters high. And we're going to try to do a lot more investigation of the factors that are going to affect the plume. And Martez actually discussed it. He covered that really well. The plume depth, injection depth, the size distribution of the bubbles. Those are the important things that we need to understand if we're going to be able to use this remote sensing signal to infer something about the breaking wave or about the bubble plume. And I'll stop there.
Thank you, Chris.
Thank you.
Thanks, very nice talk. Okay, so we have a bit of time for discussions now. Are there any questions? I saw some clapping, that's good. Great talk. So are there any questions for the speaker? So, I mean, if I may ask, I'm sorry, it's a very naive question, but how do you, so basically you're saying that the foam is a bit, warmer than the surrounding water because the skin of the water is breached and you water comes up from below. Is that?
Yeah, Henrik, that's exactly right. And I'd invite Andy Jessup if he wanted to say anything, but that's exactly right. Many of these techniques that we're using, Andy used a long time ago to look at breaking waves in the open ocean. And they were focused on air-sea gas flux mostly because it was a way to, under micro braking, right? So braking without air entrainment or just stressing and straining in turbulent motion below that would strain and breach this really thin, cool skin are immediately visible because of that bulk water that's now visible at the surface, or that's perceived at the surface using those thermal cameras, right? Exactly.
But I mean, if you, so you had some cases where the difference between the water temperature and the air temperature was basically zero.
Yeah.
So in this case, I mean, you don't have that difference, right? I mean,
I'm sorry, in which case?
Well, you showed what is kind of a scatter plot with some blue dots, and then there, I think it was like that the temperature differential between the air, yes, was close to zero. So in this case, the layer would have the same temperature as the lower fluid, right?
Well, this is the bulk water temperature. So this would be not the skin temperature difference, right? So the skin temperature almost always exists as long as you have some outward heat flux. Much of that heat flux is supported by the latent heat flux. So even if the air water temperature difference is close to the same, you almost always support some evaporative cooling. So yeah, that's a great question, right? And you can of course have the inverse where you get the air.
Sorry,
air is a little bit warmer than the murkier from observations in the field that you see less and less of a cool skin, but it can exist.
Okay. Just one other sort of naive question, if you don't mind. So basically, this has nothing to do with sort of energy dissipation and creation of heat, right?
No.
If you'd like, just Henrik, I think the cool skin phenomena is not central to this study because really what we're saying is that as long as the foam is being generated by the bubbles as they rise, then the bubbles at the surface are about the same temperature as the surrounding water, and that's being brought up from below. And it's really that when the bubbles stop being generated, but there's still foam at the water at the surface, the foam cools very rapidly because it has a much higher it cools much more rapidly than the surrounding water. So it really doesn't rely on the cool skin so much as the fact that the bubbles stop being the foam stops being generated at the surface because the big bubbles aren't rising anymore. And so that's the connection of the time it takes for the foam cooling to start to the time scale of the bubble plume.
Yeah, but so my question was more like, why do you have cooling? Like, why, what? So the cooling is just because you have a higher, basically, interface between the air and water. So you have, it's basically evaporative cooling, right? I mean, is that?
But the bubbles the bubbles are mostly air, and so it cools much more rapidly than the water that's undisturbed.
I see.
You have a different cooling rate of the foam than the surrounding water. But that cooling doesn't start until the cooling is delayed because they keep being generated. The bubbles are coming up and generating the foam, so that you're constantly bringing up this water from below, and so the foam is about that temperature of the water until the bubbles stop rising, and then it can cool.
I see. But
that makes a little more sense.
So it cool, but I mean, so when you say it cools, so then it actually gets to a temperature which is lower than the surrounding water.
Yeah.
That's correct.
I see.
And then it'll warm back up once the foam dissipates and becomes
I see.
non-foamy, then it's just like the regular water around.
Very interesting. Yeah.